Juan Humberto Sosa Azuela holds a PhD in computer science from the National Polytechnic Institute of Grenoble, France. He is a full-time professor at the Instituto Politécnico Nacional and director of the Center for Computing Research. He is an emeritus member of the National System of Researches, a member of the Mexican Academy of Sciences, and a member of the Academy of Engineering. He is also a senior member of the Institute of Electrical and Electronics Engineers and the International Society of Neural Networks. He is a member of the Academy of Computing Machinery and a fellow of the Mexican Society of Artificial Intelligence. In 2021, he was awarded the National Computer Prize by the Mexican Academy of Computing. In 2023, he received the Research Award at the Instituto Politécnico Nacional in the area of basic research. In 2024, he received an honorary doctorate from the Technological Institute of Ecatepec. He is the author of 5 textbooks, 13 patents, 32 copyrights, and over 500 conference and journal papers. He has given over 560 invited talks. His research interests include artificial intelligence, machine learning, artificial neural networks, image analysis, pattern recognition, robotics, and metaverses. Without further introduction, Juan Humberto Sosa Azuela.
Good morning, everyone. I would like to thank Citedi of our institute for inviting me to this seminar on artificial intelligence and quantum computing. I would like to thank all the organizers, Oscar, and of course the director of the head of this research center. And I would like to thank all of you to be here, mainly the students. You are the reason we are here. We are the reason we teach. You are the reason we teach. You are the reason we generate new knowledge. And we transform this knowledge into solutions to the problems that our society tells us to solve, to have a better quality of life. Today, I will talk about artificial neural networks. I will present some basics and why these tools are so powerful. So the content of this presentation is composed or divided in 4 parts. First, an introduction. Then I will present some related concepts to artificial neural networks. After, I will present or I will explain why artificial neural networks are so powerful, and I will give a final note. As an introduction, I will present some videos. If I cannot do it, I will ask someone to help me. I will try to do it. It's not so easy to control this. Okay, in this video, you can see 2 robots using computer vision. The calculations are done in the small computer with the robot, and you can see that the robots are trying to play football, soccer, okay? This is the first match between robots, okay? So it was in China. You see that the robots are able to watch, to analyze, to take decisions. Sometimes they fall down, okay? This is normal. Then in the next video, you see another robot and trying to do something that is not easy. From the other part, you see the robot analyzing the situation. This is very difficult for a human being, very difficult. Okay? Another one. Okay, let's see. Oops, I cannot. Okay, I see, it's here. they are still, you can see, in development. Another one. This is developed by Tesla. So the robot takes a t-shirt and folds it. Using vision, using pattern recognition, and of course, automatic control to control the movements of the hands of the robot. That's another task. This will I skip it. Here is another very interesting, which is under development. This is one of the first service robots. In a few years, this will be very common, to have robots that help us to do different tasks so we can have a better life in our homes, for example, in our working spaces. So you can see the abilities of the robot to perform different tasks. We continue. This is a final one. I don't know if it is a final one, but an autonomous car. You see, this is in some of the streets in a city in India. It performs very, very well. And okay, that's all. Okay, something common to all of these machines is that inside of them we find, among other things, an artificial neural network. Okay, artificial neural networks. Let us speak about them. They emerge as a very vague, of course, approximation of a biological brain. Where do we find brains? We find brains in animals, but we don't have brains in plants. It's a very easy explanation why we have brains in animals and we don't have brains in plants. Because animals need to move, they need to perform very complex related tasks. That's the difference. You don't see a plant moving. You don't see a tree moving. But you see an animal moving, for example, or chasing. So let us talk a little about the human brain. Our human brain is a mass of nervous tissue, more or less about 1,200 cubic centimeters and about 1,400 grams. It is composed of some 86 billion of neurons, and that's the level of connection, okay? More or less 10,000. One neuron in our brain is connected to other 10,000 in average neurons. So basic concepts. A brain, as we know, is composed of so-called neurons. One neuron has dendrites, has a cell body, and an axon. Those are the three main parts of a neuron. As in the case of a biological brain, the artificial neuron would be the basic processing brick. So in the artificial case, these are our main processing bricks. Computationally speaking, an artificial neuron is represented as follows. As you can see, you have two vectors, this input vector, this weight vector, and at the output of the first part of the neuron, you have a scalar, A, which is obtained as the dot product of these two vectors. And then you take this scalar and you put it here inside a function, normally a nonlinear function, to produce your output, okay? in all neurons, these are the three main mathematical components. Activation function. The activation function is the operation that takes the input vector and that maps to the output, as shown here. Which is the goal of an activation function? Is to introduce nonlinearities to the neurons and, in consequence, to the whole artificial neural network. Without these nonlinearities, the neuron would not be able to learn nonlinear functions. Why? Because if we go back, this is a linear operation. So if you want something nonlinear, you have to introduce it at this level. Okay, we continue. This is an example of a three-layer neural network. As you can see, in the input of the neuron, you have a layer composed of this number of neurons. You have your input vector, which goes in this direction, is processed with these operations, and then you have as an output, you have another vector, which is this one. Then you take this vector A1, you process it through these S2 neurons, and you have as an output another vector. Then you take this vector, you process it, and at the end, in this example, you have a vector A3. So at the end, what you have? You have a mapping from that input to this output. For an artificial neural network to be useful, it must be trained. This means that the free parameters, the connections between the neurons of the artificial neurons had to be adjusted. Okay? The interconnection weights, as is mentioned over there, among the neurons should be adjusted automatically. This adjustment is made how? In an automatic way by means of a rule. In this case is one. For example, backpropagation rule is, or a variant of it, is very common to adjust in a cyclical way the parameters, the connections between the neurons. And now you know that you can use these tools to predict, to classify, to estimate parameters, to control processes, and so on. So the applications with the same tool are enormous, are very big. Let us talk a little about generations of artificial neural networks. So from 1940 to 1960, the first models were developed. These models take as an input a vector, and they allow a mapping of this vector to two levels, AB, for example, A01 or -1 plus 1. That's the first generation of artificial neural networks. Second generation neurons from 1960 until now allow mappings from an input vector again to a subset of R. For example, a subset between 0 and 1 or -1 and +1. And third generation neurons, which are being developed now at this time, apply multiple operations, for example, correlations between vectors of values, which are spaced spatially temporally. So, first generation neurons. These neurons, or these bricks, combine two operations. A linear operation, which is produced by the dot product of two vectors, the input and the weight vector, plus an activation function to obtain the desired output. In this case, as you can see, y equals 1 if this is accomplished, or 0 if this is accomplished. Or this is another example. So these models were used from 1940 to 1960. Second generation neurons, which are used right now at this moment, combine again two operations. The same dot product, which obtains this scalar, and then you put this scalar here into an activation function which is nonlinear. For example, the sigma function or the tan H function. These are two examples of activation functions. And third generation neurons combine multiple operations, as I mentioned, for example, correlations among data. For example, in our laboratory, in one of our laboratories in our research center, we are working with these kind of models now. What is the dot product? Just to remember. The dot product uses the sum operator here. It takes two arguments, as arguments two quantities, two vectors, these two. And then with these two vectors, you perform the dot product, and you obtain the scalar A. So computationally speaking, this is the same as this. And the value E, the value of A, as we know, could be positive, could be negative, or 0, depending if the vectors are aligned, are perpendicular, or are not aligned, okay? The output of the neuron, Y, is obtained by substituting the value of the scalar A into the selected artificial activation function. For example, if we use the sigmoid function, then you get the output as shown over there. It will produce a value between 0 and 1. So, taking this into account, and we know that artificial neural networks are used everywhere, even in our phones. In our phones, we have artificial neural networks, okay? We can establish the following question, and which is this question: why artificial neural networks are such a powerful tool? For example, we know that a Ferrari is much more powerful than a Volkswagen. Why is much more powerful? There is a physical, there is a mathematical explanation why this auto is much more powerful. Okay, I took part of the information to prepare this presentation here. And artificial neural networks are very powerful tools and can be used for solving almost any statistical learning problem with very good results. Why? Why artificial neural networks are more powerful in most of the scenario than other algorithms when we compare them? Okay, there is a mathematical reason for this, and I will concentrate I will try to do it in a very easy way to explain this reason. This is the small question, okay? In a very simple way, the set of functions that we can approximate by means of an artificial neural network is very, very, very big. It's not infinitum, okay? But it's very, very big. That's the small answer. So what does it mean to describe a function? See, here we have two things: describe and very big. So what does it mean to describe a function, and how such a set of functions can be so big? Okay, so we go and we are going to see, or we're going to talk about a little bit about machine learning and how we can see this problem as a function approximation problem. So what is machine learning? The machine learning problem can be stated as follows. So suppose we have a set of data, okay, as shown here, where our X is a datum, it doesn't matter which kind of data, and Y is a related observation with this datum. Y can be a real number, it can be a distribution of probability, for example. And the problem consists, at this written over there, you can see there, on finding a function f for which, when we take the input and we put it here, is approximately this output. That's our problem. For this, for example, how do we solve the problem? For this, we fix in advance a family of parameterized functions. We then select a configuration of parameters of this function that best adjust f. For example, in the case of a linear regression, this family of functions use this equation, where a and b are the parameters to be adjusted. An example, if we have only one input and one output, which is the model that describes the following data. If you analyze your data, you can see that your model is this one. So your parameters to adjust are W1 and W2. If you observe the relations among the input data and the output, you can verify or deduce that your model is this one. I mean that W1 equals 1.8 and your second parameter equals 32. Very easy. You have much more examples. Once we have the model for this data, you can predict any other value. For example, if X equals 52, then Y is 125.6. If we suppose that there exists a function, let's say G, that allows relating the input with the output, the problem can be restated as an approximation of functions. Okay? And this takes us to the field of approximation theory. So I will give some words on approximation theory. And for this, I will use an example. Suppose we have to approximate this function. We have this function, where E is the famous Euler number, and we know that this is a transcendent function. We cannot calculate this value by means of a finite number of additions and multiplications, but we can do is to approximate this function as shown here. And what is that? That is a polynomial, and through this approximation, our value of E can be calculated. How? The bigger is n, the nearer will be the approximation of E to the true value, okay? Now, if we have a function G, the goal is to select among a family of functions one which is simple and sufficiently near of G, okay? So we need something very simple which is near of the desired G. An approximation function, we have to answer three questions. What is sufficiently near? Which family of functions we should use for that approximation? And third, for this family of approximation functions, which one we should select? So we have plenty of options, and we have discovered that a particular case of these approximation functions to answer these three questions are artificial neural networks. At the beginning of the investigations, researchers didn't know this. Now we know this. So let us give some words how artificial neural networks can be used as approximators. Again, we have a function G, that describe the relation between a set of data, a set of input data and the observations, such as G, taking this input as an argument, we obtain this. So the task consists of finding a function that accomplishes two things. It generalizes the knowledge of the data. It means that once we have trained it or we have obtained it, we can use a different data to test it. And second, that is computationally feasible. Okay? So we can implement it, for example, in a computer like this. If we assume that all data is part of a subset X, for example, this one, what would we like? We would like a function such as the difference between these, when we take the supreme, is as small as possible. That's what we want. For an example, just to understand the meaning of this, we can imagine this quantity by plotting our functions. This is the function, the blue one is the function to be approximated, and this orange one is the function that tries to approximate the blue one. Okay? So we take point by point the difference between this point, this point, this point, this point, this point, this point, and we begin to color in blue. And as you can see, we have an area here, we have an area here, an area here, and an area here. Okay? We compute all of these areas, and we take the sum of this, and this is our error. Of course, if our orange function is exactly above the blue one, our error is 0. Okay? So the question now is, which set of functions we should use to get or to obtain that approximation? One option we know now that is an artificial network with one hidden layer. An artificial neural network with just one hidden layer is enough, and we will show it later by a theorem, is enough to approximate any continuous function. So what is an artificial neuron with a hidden layer? Is this one. So we have here a perceptron, okay? We have our linear function here. We have a weight that multiplies this value, and then we take the sum all of these n results. Phi is a nonlinear function. What we know is called the activation function of each neuron. An example is, for example, the Sigmoid function. And the value of x corresponds to a datum, while w, b, and v are the parameters of our artificial networks that need to be adjusted. If you do not understand this, then certainly you can understand this. It's the same thing. Okay? This equation is this graph, is this design. It's the same thing. We continue. One important question would be the following. Is this family of functions what we require to approximate any function in a reasonable way? The answer is yes. It's very interesting. So, proven fact. We will see by means of a multi-layer artificial neural network, we can approximate any function if we have enough. What is enough? Okay, we will see what is enough. Enough neurons in the intermediate or hidden layer. In general, we do not know how many layers and how many neurons per layer you need to add. But the so-called superposition theorem or universal approximation theorem has helped us a little bit in this direction. So which is the universal approximation theory? So I recommend you strongly to read this paper, okay, by Chivenko, 1989. Approximations by superpositions of sigmoidal functions, mathematics and control, mathematics of control signals and systems. Here you have, and here is what you obtain. And if you read the paper, you will find more or less what I will explain next. So let us talk a little bit about the superposition theorem and its application to the design of artificial neural networks. So in a very vague way, in principle, by means of an adequate combination of perceptrons accommodated in 3 layers, one input layer, one hidden layer, one output layer, you can synthesize any separation function, which is the background, the approximation of periodic functions by means of Fourier series. That's the basis. We know that the more components we add, the more precise would be our approximation. So the superposition theorem dates from 1957, Kolmogorov. In an informal way, Kolmogorov's theorem established that an artificial neural network composed of 3 layers, one of input, one intermediate, and one of output, of processing elements can implement any continuous mapping function. In a more formal way, given any continuous function f, as shown here, it can be implemented in an exact manner by using a feed-forward 3-layer neural network with n inputs at the input layer, 2n+1 neurons or nodes at the intermediate layer, and a node at the output layer. Another way to establish this important result is as follows. Modified version. There exists a set of increasing and continuous function h, p, q, such that each continuous function f can be written exactly by this equation, where g are continuous functions or one variable which are appropriately chosen. And that's the problem. You have to choose it, you have to select them in an appropriate way. In 1963, this mathematician Sprecher shows that that function, which these functions here, can be represented as shown here, as a product here, and the value of lambda is between 0 and 1, and each h goes from here to here. 3 years later, in 1966, this another mathematician, Lawrence, shows a very important fact. Thus, this h could be the same. And with this, you have a very good simplification of the artificial neural network. It means that you can use the same processor. Taking this into account, a modified version of the theorem that takes the name of the 3 scientists can be established as follows. Kolmogorov, Sprecher, and Lorentz theorem. For each n greater or equal than 2, there exists a continuous function h, and these counters and positive constants lambda, such as the following is true. For each continuous function f that goes from C to R, there exists a continuous function g such that this is true. Okay? One characteristic of this result is that it's an existing result. So you know that your artificial neuron exists. Okay? Unfortunately, this is not a constructive tool. You have to build it. the transfer function of the intermediate nodes are similar to one weighted sum, while the activation function of the node is highly nonlinear. That's what all we know. So which are the steps to select our approximating function? First step, I will do it with a graph. Suppose that this is the function you have to approximate. You select an epsilon, which is the size from here to here and from here to here. And when you plot a strip which is bigger, which is wider than your function. So your function to be approximated is inside of this strip. Of course, the smaller is epsilon, the better will be our result, because this strip will be much more, how do we say? Narrow. Thank you very much. Okay, step 2. You propose an approximation function, a 3-layer neural network, and you put it inside your strip. For example, that one. So this is the function to be approximated, this is the function that approximates, and you select different values for W, B, and V. For example, if you put them at random, you have a function like this, but you have an infinite number of functions, of examples. Our theorem guarantees the existence of a realization F. This family of functions is known with the name of universal approximator, and this is what gives the power of artificial networks. But because inside of a box with a chosen epsilon, we have an infinite number of orange functions that could be approximations of this blue function. I will show an example. The main feature in practice is that we never know the approximation function. I will explain that later. But what we know is that we have access to the data. In all machine learning problems, what we know is we have data. We have sounds, we have images, we have data in general. There is an infinite number of possible configurations depending on the values of the parameters we have. For example, we can have this one. For example, we can have that one. Or for example, we can have that one. Of course, most of these approximate the data in a very bad way. This problem of this phenomenon is known as overfitting. What we would like is something like this, which is near the blue one. That's what we are looking for. So the useful version of this result to approximate but by means of arrangements of perceptrons is the following. Let G a continuous, monotonically increasing, non-constant, and bounded function. And all of those things there, at the end, given a function f and a epsilon greater than 0, there exists an integer m and a set of real constants w, p, and theta, such we can define f as a realization, capital F, as a realization of f such that that is bounded, or is less than is always inside your strip. The good news is that the universal theorem for a function is applicable to the perceptron. Why? Because if you take, for example, as an activation function your sigmoid, the sigmoid function is non-constant, is bounded, is monotonically increasing. What does it mean? That it satisfies the conditions imposed by your theorem. If you use your tangent, it's the same thing. The resultant net has n input nodes, a hidden layer composed of m neurons, and the equation represents the output of your artificial neuron as follows. You have n input nodes, one hidden layer composed of n nodes, and the inputs are denoted as shown here. Your J hidden neuron has these weights and one bias, and the output of the neuron is a linear combination of the outputs of the hidden neurons with this W as the synaptic widths between the neurons of the hidden layer and the output neuron. That's our neuron. What I said here is the same as this. For example, suppose you have to have a neuron that implements the XOR function. You take n as 2, you take m as 2m plus 1, which is 2 by 2 plus 1 is 5. With that, you have your result. You can add more neurons, you can subtract neurons, and to verify if you can approximate this function. According to what we have seen, by means of an artificial neural network, we can approximate any function. For example, that one. We have seen that no matter what function we have, for each input, the value of fx is given by the output approximated by the net. For example, you can use an artificial neural network composed of one neuron at the input, 3 neurons at the hidden, and 1 neuron at the output. This result provides a certain kind of universality. No matter what function we can approximate, we know that by the theorem, there exists an artificial neural network that can do it. This does not mean that the artificial neural network can compute any function in an exact manner. We obtain a very good approximation. What we obtain is an approximation as good as we want. How? For example, by increasing the number of neurons in your hidden layer. For example, if you have, as an example, this function to be approximated, you can obtain a better approximation by increasing the number of neurons in the hidden layer. Of course, there is a problem here. This net does not explain by itself. What do we mean by that? Although you can approximate in a very good way this function, you cannot say directly by using your artificial network that the generating function of this graph is this one. Okay? You have data from to have an approximating function. You have your artificial neural network, and we know by the theorem that by means of this artificial network, you have a very good approximation, but not an interpretation. What is an interpretation? To obtain this. To obtain that, you have to take the knowledge that is represented here and use, for example, an explainer, which takes us to the area of explainable artificial intelligence. And with this tool, there is a lot of investigation right now in this direction to obtain a set of rules or to obtain a mathematical model. Some ideas to take into account. Suppose that you want to approximate that function. If you increase the value of I, you get mod periods of your function inside the interval, this one. So suppose you use an artificial neural network composed of one input, two neurons in the hidden layer, and one linear neuron at the output layer. With this, you can obtain an union, the union of as many sigmoids as neurons you put inside here. So which is the capacity of this particular neural network to approximate a function? You see that for I equals 1, the net approximates very well. They are superposed. So for E2, for E equal 2, you obtain a very good approximation. For E equal 4, you obtain a very good approximation, but you began to have a small approximation problems. Where you increase, you go to 8, and with this neural network, you do not get a good approximation more. Okay? So which is the capacity of this particular neural network? E equal 4. That's your capacity. So we are going to go in another direction. We have, for example, this function to be approximated, and we are going to increase little by little the number of hidden nodes. So, for example, what can we do with an artificial neural network composed of one input, two hidden nodes, and one output node? And this is our function to be approximated. So if you take this neural network, you can see that you don't have a very good approximation. So we can increase to 3, and with 3 neurons in the hidden layer, you get a better approximation. We take 4, we are almost there. And with 5, you have the approximation you want. So, which is the conclusion? Unless the number of neurons in the hidden layer is not at least 5, for this particular case, you don't get a good approximation. Mm-hmm. So in short, this is just to show you, and that's what it does any artificial neural network today. Why artificial neural networks are so powerful? Because they can approximate functions. So if you can establish your problem as an approximation of functions, then you can solve it by an artificial neural network. That's the conclusion. It doesn't matter if your problem is of prediction or classification, parameter identification, or control, process control. We have already seen is that in principle, by an artificial neural network composed of one input, any n hidden neurons, and one output, you can do the job. Final note. Why neural networks are important today? Well, you know that last year, the Royal Swedish Academy of Sciences decided to award the Nobel Prize in Physics to Professor John Hopfield and to Professor Geoffrey Hinton for their foundational discoveries and inventions that enable machine learning with artificial neural networks. We know that this year, the same academy awarded 3 colleagues with a Nobel Prize in Physics for the discovering of the tunable effect in quantum computing. So at that moment, we know that something is important. So what is my suggestion? To work in artificial intelligence or quantum computing. And we have to recognize that artificial intelligence, talking about artificial intelligence, is here to stay, and there is now a lever to be a powerful development of our country. So as a country, we use artificial intelligence, and of course, quantum computing, we obtained this. This image was generated by ChatGPT, of course. So thank you very much.